All right, today we're going to turn our attention to reactions. So far up to now, all we've been talking about is putting sort of hot things into liquids or cold things into liquids and watching the heat exchange. But of course, this is chemistry, and we want to see how reactions can gain and lose heat. So our goal is to kind of turn our attention to reactions and also to be able to use a reaction coordinate diagram to represent the enthalpy change in a reaction. So obviously, we're going to have to introduce what enthalpy is. So what we're talking about here is an enthalpy diagram looks kind of like this. And you know, how we represent this will depend an awful lot on whether the reaction is exothermic or endothermic. You'll see it's pretty easy. Okay, so we've been taking hot metals up to this point and dumping them in water, but we're not going to do that. Today we're going to take a little bit of calcium chloride. And if you were in class this week, I might have had you do this as an introductory activity. If you weren't in class, we're going to have you measure the heat exchange of a reaction with some other chemical later. So the point here, though, is that this chemical, right, this reaction that we're doing is really just the dissolving of calcium chloride, which would look like this, right? We're dissociating those ions. But you can see like the chemical powder and the water are both pretty much at room temperature. I mean, the water is actually a little colder here, but they're pretty much at room temperature, right? It's not like that scalding hot metal which we dumped in there. Yet when we go to dump that powder in there, we are going to see some sort of heat exchange. And so sort of the essential question today is why? If they're both essentially at room temperature, why would you expect that? So let's look and see what happens here with this one. You dump it in and you can see pretty darn quickly, even before I start stirring this, that the temperature is already rising. This is clearly an endothermic or exothermic reaction. Well, it's definitely an exothermic reaction, right? You can see the heat is rising in the water, and this gets to system and surroundings once again, which is the chemical is the system, the water is the surroundings, and the water's warming up, which tells you heat has to be coming out of those chemicals. If we were to do the exact same thing with ammonium nitrate, you can see that ammonium nitrate, another white crystalline ionic solid, does the exact opposite, right? You see the temperature start to go down, which tells you it's endothermic. Is heat leaving or entering the beaker? It's definitely entering the beaker, right? If the water is cooling down, that means the chemicals are pulling the heat into the chemicals. Now, the natural question might be is if water is kind of leaving, or if heat is leaving the water and going into the chemicals, are the chemicals warming up? And the answer is no, they're not warming up. So that is something we got to get to today. It involves potential energy. We'll see that a little bit later. But before we get to that, do me a favor. Would you write in what is the reaction we're doing here if this is the dissolving of ammonium nitrate? I want you to write a reaction in. All right, so is this what you got? Yep, it's just the dissociation of the ions, right? So representing dissolving as a reaction is, you know, I mean, you can do it. You just show the ions dissociating. All right, so what we're saying here is that chemical reactions can be endothermic or exothermic. The one that warmed up the water clearly is going to have a negative sign because the heat is going out. And it turns out that the amount of heat released by calcium chloride as it does this is about negative 81 kilojoules per mole. It's been measured many times. You can look it up in books. And the endothermic reaction we did, the one that cooled down because heat was coming into the reaction, it was positive 26 kilojoules per mole. Now you'll see there's this new symbol here to represent endothermic and exothermic processes, but the sign thing will not change. Negative signs still mean heat is leaving, and positive signs still mean that heat is being absorbed. We still have that sign convention of exothermic and endothermic. That's why we started with signs. But this delta H thing is referred to as the heat of the reaction or the enthalpy of reaction. Or you can just simply say delta H. They all mean the same thing. And delta H is the symbol that you use when you're talking about a reaction. It means more or less the same thing as Q. It's just when you're talking about reactions, instead of just hot metals or cold metals, you use the enthalpy of reaction symbol. It's customary to put a little label on the bottom of it. Like these were both dissolving reactions. So you could put DISS if you wanted to. People tend to use SOLN, which means for solution, making a solution. So both of these would be delta H's of solution or heats of solution. If you are doing a reaction, which I suppose we are, you could say delta H a reaction as well. This is the most generic version. Or you could be specific. If you were doing a combustion reaction, you could say delta H of COMB, right? If you were doing a single displacement, you could say delta H of SD. You tend to put a little label on it to represent what it means. Yeah, so delta H is enthalpy, and enthalpy is just the heat of reaction. So the question is, if they started at room temperature, if the powder started at room temperature and the water started at room temperature, how the heck did that powder warm up the water? Or in the other case, how did it cool it down? And of course, the answer has to do with potential energy, right? So potential energy is there in some way. It's the same sort of thing, like if you were sitting there thinking, how can a chemical have potential energy? I can understand how roller coasters can have potential energy, but how can chemicals? Well, if you think about it this way, right, if you talk about liquids, just chemicals, you talk about water or gasoline, right, I suspect that you would feel a little bit less comfortable holding one of the two of those real close to yourself. And I'm hoping that's gasoline. By the way, if you type into Google for a picture of somebody holding a gasoline can, you can actually obviously find it. I'm not sure why she looks so comfortable though, because I don't know about you, but since potential energy is the energy for something potentially bad to happen, it's surprising to me that she's looking so comfortable here. Clearly there's more potential energy in this can than there is in water, right? Water has significantly less. In the same way that if you were holding a bowling ball above somebody's head, it might not be moving, it might not be, sort of crushing your head, but there would be a lot of potential energy due to gravitational potential energy, right? Because it's above your head. Well, this isn't gravitational potential energy stored in here, it's chemical potential energy or bond potential energy. So we believe there's some sort of potential energy stored in that container. Think about it this way. If you were looking at these two cars and they both didn't have working brakes, which one of the two of them would you be more worried about the outcome of? Well, I don't know about you, but this car has significantly less potential energy because it has low gravitational potential energy. This has high gravitational potential energy. And so therefore, if you didn't have brakes, there'd be much risk of this turning into kinetic energy, right? Whereas this one has very low potential energy, so you're not going to get much kinetic energy. Same thing goes with chemicals, right? The gasoline has a lot of potential energy stored in the bonds, and the water doesn't have very much at all. So it does relate to the roller coaster idea. It's the same thing. When an object goes from high potential energy to low potential energy, it releases that energy. But the thing that we need to know is if you've taken physics, most of that potential energy that you've looked at in physics turns into movement energy, turns into kinetic energy. But here we're talking about heat energy. It turns out the two ways to release those things are work, which goes into kinetic energy, and heat. Symbol for work is W, symbol for heat is Q. This is what physics is primarily about. This is what chemistry is primarily about. But know that actually chemistry does care about work. If you take further courses in chemistry, you'll learn more about work. And physics definitely cares about heat. It's just in AP chemistry and AP physics, it tends to fall out that most of AP physics is about work and most of AP chemistry is about heat. But those are the two ways to exchange energy. The other thing that you should know about potential energy is it's the difference in potential energy that matters so much. Like here we're at high potential energy, there we're at low. You could say the difference here is, 10 kilojoules or something like that. Well, it would be 10 kilojoules whether this thing was a couple of feet off the ground or whether it was really high off the ground, like up here. We often are interested in the change in potential energy, which is why we refer to delta H as delta H, is because we can't really measure the actual potential energy. We can only measure the change in enthalpy. Okay, so if potential energy in the gasoline can is pretty high, then it can be turned into heat energy, or it can be turned into kinetic energy as well. Like imagine this tanker truck here has a whole bunch of octane in it, has a whole bunch of gasoline in it, right? It can radiate heat out which by the way from the gasoline's perspective would be negative. We'd call it delta H because it's an actual chemical reaction, not just a hot block. But the other thing that could happen is you could get a little bit of work done too, right? Work would be actual physical destruction of the property, pushing things back physically, right? So that's what I mean about heat and work are two ways to transfer energy, but in AP Chem we won't look at work at all here. Now, what is the delta H of octane burning? Well, octane is a combustion reaction. And you remember, we can put a little label down here, delta H of combustion, or we could just say more generically, delta H of reaction. In any case, it's negative 5,500 kilojoules. Is it endo or exothermic? Well, definitely exothermic. Because of that negative sign, heat will be radiating out, and that's how much heat will be radiating out per mole of octane that reacts. So all combustion reactions turned out to be exothermic. Every single one of them. It's one of those guaranteed things. But if we were going to represent them with a reaction coordinate diagram, an enthalpy diagram, we'd have to decide which of these, the left one or the right one, would be a better representation. Now obviously I'm going to explain it to you here in a second, but I want you to make a prediction. I want you to look at these two diagrams and try to see what they're representing, and I want you to see if you can give a reason for why you think A or B is a better representation of combustion. Well, one simple way to do it is to look at this reaction and say, if the delta H is negative, right, clearly that delta H is going down. That means that I think this looks a little bit more appropriate, right? As in, it seems like the delta H is losing energy. That's one way to do it. So this one would be positive something, right? The other way to view it is the reactants, which are these two, must be higher in energy than the products. Why? Because they gave away energy. Think about this as like these are kids that are hopped up on sugar. They give away energy and they're really sad afterwards. They're much lower in energy afterwards because they gave up all that energy. So in other words, you would not be worried about walking around here the day after this explosion because whatever chemicals are left are very low potential energy. So in an exothermic reaction, the reactants are higher in energy than the products, and the delta H, the enthalpy of the reaction, is the difference in energy between the reactants and products. Now this little hump here is referred to as, and I want you to get it in your notes, the energy of activation. This is one of those moments where it's a kind of a chicken and egg problem. We don't know, we have to do one topic before the other. But this energy of activation, which is measured from the reactants to the top of this little peak, what it tells you is it tells you how fast the reaction occurs. And so you don't actually at the moment have to include this little hump. A lot of times you'll see people include it kind of like that. Because you don't really know how high to draw. Do I draw it real tall like that? Some people will just go straight down sort of like that until we get to kinetics. It's up to you, but just wanted to make you aware of that. So that's a reaction coordinate diagram. You notice it's not terribly mathematical. The only mathematical thing about it is the difference in energy between the reactants and products, which is the enthalpy. This is the reaction progress, as in we start with reactions, right? This is the start. This is the end. It's not very numerical, right, in that way. It's only numerical for the delta H, the difference in the reactants and the products. Okay, let's keep going here. Why don't this thing click? All right, so exothermic reactions, they tend to be what I call favorable. And what I mean by that is, let me get this back. What I mean by that is there's a natural direction to things in life, right? For instance, nails rust. Rusty nails do not become clean, right? Your room naturally gets a little bit messier. You have to do some work to get it clean. It's not like you can't do things in the unnatural direction. For instance, exothermic reactions tend to be favorable, and I like to think about it a little bit like skiing. Unfavorable. So here we are at the top of the hill. It's pretty easy to ski down a hill, right? That's the natural direction. Can you start at the bottom of the hill and work your way up? Yes, of course you can. You've seen people who strap their skis on and hike up mountains, but it takes a lot of energy to do that. The more favorable and natural direction is downhill, and the same is true for enthalpy diagrams. All right, now let's look at this one. We did this one a little bit earlier. I want you to pick out, do you believe, based on what you're seeing here, is enthalpy diagram 1 or 2 going to be the more natural one? And of course, give me a reason for why. All right, so hopefully you got enough evidence there. Well, this reaction is definitely going to be endothermic, right? It's definitely going to be endothermic, which means because it's endothermic, it's delta H. Ooh, I almost said Q, but this is a reaction, no Q's here, right? That means that if it's cooling down, the water is losing energy. The water is losing energy to the chemicals. Let's say that's a chemical particle right there, right? So from the water's perspective, it's losing that energy, but from the chemical's perspective, it's gaining that energy. Oop, I'm going to go delta H because it's a reaction. And so it's got to be a positive delta H, which means if we had this reaction, I think this one is ammonium nitrate. If we had this reaction and we say delta H is positive, that means that if you have the reactants and products, if it gained energy, these must be lower in energy than those, because it gains energy, these are going to be higher. So I think one looks better. Here's your ammonium nitrate, and your products are going to be higher in energy because they're gaining that energy. Okay, so that's a better reaction coordinate diagram. And this would be the delta H between the reactants and the products, and it would be positive. Actually, we had it on the other page. I think it was about 25 kilojoules per mole. Obviously, we're going to get to measuring that with calorimetry pretty darn soon. Okay, so that's how we draw reaction coordinate diagrams. Is we essentially look at what's happening in the reaction, and we figure out which way we should have the reactants or products go. So let's say that these are the reactants. Based on what's going on here, I usually start in the middle. This what should be on this axis down here? Extent of reaction, or as the reaction goes. So you see that reaction is warming up. That means the heat is coming into or out of the beaker. Definitely heat is going out of the beaker, so the delta H of this reaction is negative. It's exothermic, and that means if heat is going out, if you have the reactants and you have the products, the reactants will be here. Will the products be higher or lower in energy than the reactants? Well, if heat is leaving, the products are going to be lower in energy than the reactants, and we draw a reaction coordinate diagram like that. How would we label the delta H? It'd be from the reactants to the products, and our delta H would be negative something. Who knows? 100 kilojoules per mole or something like that. Okay, so the last thing we got to do here is we've got to learn to write thermochemical equations. We know how to look at reaction coordinate diagrams, but what's a thermochemical equation? Well, we've sort of been writing them up till now. Like here's hydrogen in a balloon. If you explode, it's clearly very, very endo or exothermic. Well, definitely exothermic because it has a negative 106 kilojoules per mole. It'd be nice if I said that. So this kind of is a thermochemical equation, but a thermochemical equation is where you include heat in the reaction. So let me show you here what I'm talking about. Like here's an example. Here's the same one we just saw. This hydrogen balloon reacts with oxygen to make 2 waters, and we have 106 kilojoules of energy being released. So you see what's going on here is when you include the energy in the reaction, you don't put a negative sign on it, because whether it's a reactant or a product tells you whether it was gained or lost. So here's how it works, right? Is if energy is a reactant, what we're saying is this reactant and 290 kilojoules of energy react to form this. So you might wonder, well, where's the 290 kilojoules of energy on this side? Well, it's in these chemicals, right? So 290 kilojoules of energy and mercury oxide react to form these two. So mercury oxide is down here, mercury is up here, oxygen's up there. It gained, its delta H was positive 290 kilojoules. Whereas up here, if we put the energy on the product side, notice no negatives ever here. we're saying that these two chemicals, hydrogen and oxygen, are the reactants, and they react to form water and 106 kilojoules of energy, as in this much energy is expelled. So that would be delta H equals negative 106 kilojoules of energy. So if you include it in the reaction, there's never any negative sign. If you include it on the side, then you need to put the negative sign because you don't have sort of where it's located to tell you whether it's positive or negative. So you don't ever want to put, you would never do that. Don't do that, right? No negatives ever. Super important. So exothermic reactions, energy values written on the product side. Endothermic reactions, energy values written on the reactant side. Let me give you a metaphor for this, because sometimes this can be difficult. If I said to you, we go back to my money and you situation. If I said, I have this reaction, I'll tell you what these mean in just a second. So this is possibility number 1 and possibility number 2. Right? If I said to you that these situations apply to you, and Y is you, and M is money, is it scenario 1 or scenario 2 that you think would be better, and why? Well, definitely scenario 1 is better. If you think about it, this is you and money. You're separated from each other, and over here is you with your money, right? Money is part of you. So this is you gaining money, right? And just like endothermic reactions, money, right, would be the energy that we're talking about. The energy is on the left. Whereas here's you with money, and this very sad thing happens. You would not be happy at all, right? You get separated from your money. If money is energy, if money is on the right side of the reaction, then you have lost your money. Okay? So just kind of a metaphor to help work that out, because this can be something that's difficult to wrap your mind around. But at no point would we put a negative sign in here, right? This would be an energy that would be, let's say, positive M, and this one down here would be negative M. If we write it on the side, we have to include those in there, but not if we include it in the reaction. So the important thing here is never, ever, ever use a negative value when writing the energy into an equation. Okay, let's practice this just a little bit. So what I want you to do, I'm going to leave it as an open-ended question here. Based on what you see on the screen, which side of the equation should we put the energy on, the left or the right? Is the reaction endo or exothermic? And what would the beaker feel like? Well, being that it's exothermic, because of negative sign, we know it's going to be giving off heat energy. If it's giving off heat energy, that means we have to put our 394 kilojoules on this side, because it's giving off energy. And what would the beaker feel like? Definitely warm. Let's try another one. All right, so I've got a lot here. I want you to read this, and I want you to put your answers into the document. The reaction coordinate diagram you may have to draw on a separate piece of paper, but go ahead. Okay, so we've got this reaction going on here. All we have is a thermochemical equation. Remember, we have to decide whether this is positive or negative. I'm going to write it out here on the side. The fact that it's on the left side tells me that these two chemicals are gaining that energy, right? If this is you, and that's money, this is you with money over here. Remember, the energy is in these chemicals. So I have a feeling you're gaining money or gaining energy here. So I'm going to say positive 18 kilojoules. So the reaction is definitely endothermic. How would it feel to the touch? Well, to you, cold, because the reaction is absorbing the energy. And where is it getting it from? From you. What is the sign of the energy term when written in this form? Definitely positive. And then draw a reaction coordinate diagram. So I'm going to start in the middle here. I'm going to be specific with my chemicals. These are the reactants. And would the products be higher or lower in energy? Well, they're gaining this energy, so they definitely would be higher, like that. And we have Fe, O, and CO2. It's a great reaction coordinate diagram. Ooh, let's label it as the reaction goes, or extent of reaction. As the reaction goes. That's probably not the best grammar. We'll go with that. This, I would either say potential energy here or enthalpy. Right? Either one of those would mean more or less the same thing. Let's try another one. Okay, so we've got this reaction. I want you to answer the questions in your Ed puzzle. Okay, well, they said it's exothermic, therefore it's going to be negative because heat's going out, definitely. Draw a reaction coordinate diagram, boop, boop. And you know here where I'm going to put enthalpy, I'm going to say as the reaction goes. That's the lazy way to say as the reaction goes. Here's my reactants. If I were going to put products, well, it's losing energy. So that means if it's losing energy, the products have to be lower in energy. And they said label the delta H, so I'm going to go from reactants to products. It's going to be negative something. And then it says, is the reaction favorable or unfavorable? Definitely favorable. You remember that it's kind of like skiing. If you go downhill, it's way easier than if you have to gain energy, right? That's much harder. I would not say it's a downhill reaction. It's a favorable reaction because the delta H is negative. Let's try another one. Okay, so this one, I think what they're getting at here is there's no sign. We have to decide the sign. Well, based on this enthalpy diagram, it's clearly positive or negative 52.3 kilojoules per mole. Kilojoules per mole. Well, it looks to me like the reactants are lower in energy than the products. They're going to have to gain it. We know it's endothermic. And so if it's endothermic, it's got to gain it. Which side should we put the energy on? Left side, definitely, because it's gaining. Just like you gaining money, right? It'd be you plus money becomes you with money on the other side. So 52.3 kilojoules per mole. And we've written a good thermochemical equation. Let's try one more. All right, go ahead and take a stab at that. Ooh, my arrow's a little bit off, but you'll forgive me for that. All right, is the reaction endo or exothermic? Well, it has a positive sign, so we know it's endothermic. What would happen to the temperature of the surroundings while the reaction's going on? They would definitely be getting colder because the reaction's absorbing energy, right? So the water would get colder, your hands would get colder. Draw a reaction coordinate diagram for the reaction. Well, let's go. I'm going to go enthalpy or potential energy. I'm going to say extent of reactions. Here's my reactants. And should the products be higher or lower in energy? Well, they gained energy, so therefore they've got to be higher in energy. And the delta H would be from there to there. And it would be positive 1418. We did a good job. And then what would be the enthalpy of combustion for ethanol? Ooh, tricky one. Draw a diagram of the reaction. You notice this reaction is that reaction, except for its arrow even more wonky. Just kidding. What's the difference between these two reactions? Well, one is exactly the backwards of the other. So if this one has to gain energy, that means this one would have to lose energy. And you'd say, how much energy? Well, I bet it would lose negative 1418 kilojoules per mole. So which direction is the more favorable direction? Well, definitely this one. This is the more natural direction, which I think makes sense because this is a combustion reactions, and combustion reactions are always favorable. They're always exothermic. So if you try to do the same combustion reaction backwards, where you take CO2 and water and make a hydrocarbon and oxygen, that's not likely going to work very well. So it's an example of how reactions tend to be favorable one way and not favorable the other way. All right, last one. So go ahead and answer this question. Is the reaction endo or exothermic? Definitely exothermic because the heat's on the right side. Delta H equals negative 199 kilojoules. And well, there we go, 199 kilojoules like that. Nice job.